and welcome to SciLux, the podcast where we talk about scientific developments and technological changes in Luxembourg, as usual, proudly powered by Research Luxembourg and recording at the Media Center of the University of Luxembourg. And in today's episode, we are back from holidays, actually second episode back from holidays, and our guest is Dr. Veneranda López Días, who is R&T Associate at LIST, so Luxembourg Institute of Science and Technology, and ESA Prospect Science Team member. Veneranda holds a PhD in organic chemistry and is currently closely looking at water in the lunar regolith, so lunar dust, we could say. Veneranda, thank you so much for coming today.
Thank you so much for inviting me and giving me the opportunity to be here.
We're going to talk a lot about water today. So, when you're drinking water, we're just drinking it right now. Do you actually manage to ignore the fact that this is also something you study, or you're always thinking about it as, H2O or whatever other element?
Good question. One thing is, if we think about water, the water that we are drinking right now, it could have been cycled by dinosaurs and by bacteria even, because all water we have on Earth is extraterrestrial, and it has cycled by rocks, by rivers, by humans, bacteria, dinosaurs. So when you drink water, think about now. Maybe you will not see it in the same way. No.
Of course, but it's actually difficult then, to enjoy your glass of water. Okay, so I mentioned we'll be looking at water on the moon, but we first have to start with Earth, obviously. So tell me a bit about the water cycle on Earth. I think this is something we always study. Everybody studies at school, but I don't remember anything.
Yeah, it will be interesting perhaps to talk about the water cycle on Earth and on the moon in parallel, because it's quite interesting to see the synergies between. And so, for instance, if we think about the physical state of matters of water on Earth, we have solid, liquid, and gas. But on the moon, since the pressure is below the triple point of water, we only have two state of matters. We have gas and solid, so we don't have liquid. This is quite interesting. Then, both on Earth and on the moon, the water is heterogeneously distributed. One interesting fact is the 70% of fresh water on Earth is concentrated on the cryosphere. And on the moon, the water is also concentrated on the lunar cryosphere, on the lunar poles. I will not tell you the amount of water because I want you to guess it.
And as you already hinted on that, I think this is, listeners, this is very early on in the podcast, but it's very good to start with that. Yes, we have a pub quiz question about it. And remember, the pub quiz, the way it works, if you are new to the podcast, is that we ask the question in the beginning and the answer only at the end. So, Veneranda, if you can ask the question and remember, answer at the end.
So, how much water do you think the lunar polar cryosphere could hold? I can give you three answers. Because
thank you for that. Yes.
In that way, you can have already some numbers. For instance, it could hold from 10 million tons to 3 billion tons. This is the answer A. B, from 40 million tons to 12 billion tons. And C, from 50 million tons to 600 million tons.
As I always laugh, now everybody's Googling. Now don't Google, listen to our podcast. We will reveal that and we'll talk a lot about water. So I interrupted you, said I'm not going to reveal this fact, but you can tell us a bit more, right?
Yes. So another interesting fact is how the water moves on Earth and on the moon. On Earth, we know that a big mass of water evaporates from the more equatorial regions, and then it comes back to the Earth by precipitations while the clouds are moving towards the poles. And one of the theories about how the water migrates on the moon is also that the water that is being incorporated in the more equatorial regions by micrometeorite and comet impacts, it will move towards the poles by ballistic hopes towards the colder part of the moon, like by associative desorption, and then the water that is not escaping to the space, it will all deposit again on the moon, and then by ballistic trajectories, it will arrive to the coldest part of the moon, and then store there in the permanent shadowed areas. This is one of the theories. For instance, is some similitude. Of course, there is not liquid water. It will not evaporate. It will sublimate or desorb from solid to gas, and then some will be lost to the space, and some will be back to the moon in different forms that we will talk later about.
So when you say ballistic trajectories, what do you mean actually?
Like semicircular hopes, for instance.
Mm-hmm.
Yeah.
But where from?
From the lunar soil.
Mm-hmm.
The water, it will be sublimated or dissolved, then go to the exosphere. That the exosphere is a very thin atmosphere, very, very, very thin atmosphere, similar to the last layer of the Earth atmosphere. And some of them that will have enough energy to go to the space, it will lift to the space. And the ones that don't have enough energy will land back on Earth, like semicircular trajectory.
That sounds so cool. Really?
Nice.
How do you observe that actually? How can you see? Because you said that's a theory, or we know that already?
No, in fact, there are theories and there are some modeling work. And some water was observed by remote sensing missions, water ice or hydrogen that they think that is water ice. But there were also detected some signatures from infrared and ultraviolet corresponding to water itself, the water molecule, and also to OH. So we know that the water is in different forms on the moon. Then also we can talk about it later. And how it moves is just by modeling. But the different missions can monitor the water, for instance, that is released to the exosphere from the soil, at which speed, and then also the water that is deposited on the lunar soil again. And then try to constrain those theories.
When you started getting interested in the water cycle, you do first water cycle on Earth, and then you say, "Oh, actually, I know everything. Everybody knows everything. Now it's the moon." Or is it a natural path for a geologist or a person specializing in water cycle that you kind of jump into another planet because everything is already known on the Earth, or there's something still to discover here?
My profile is quite interdisciplinary, and I move through different thematics by curiosity. So I'm chemist, and so I did my PhD in organic geochemistry, studying the local hydrological evolution by studying the peatlands, the organic geochemistry in peatlands, some biomarkers, right? And then it was mostly related to climate change. So for analyzing those biomarkers, I use mass spectrometry, gas chromatography mass spectrometry. So my first postdoc was in the development of a portable mass spectrometer for isotope analysis in water, for in situ isotopes analysis in water on Earth. But at the end, this was a very interesting topic in space, like exohydrology, like the study of water in other planetary bodies out of Earth. So it's what if we study the feasibility of adapting this mass spectrometer for space application? And space application was, wow, it was my first contact, maybe 2017 already, with the space. And at that point, I didn't know if I wanted to continue with space or with soils and peatlands and environment. And then I was so curious because it's whoa, we can, there are so many mission scenarios, not only to the moon, but Venus, Mars, asteroids. It's really, you can study the origin of life, the origin of water. So you start with water and then you can expand this really, and it's the unknown. We don't know. I mean, it's curiosity. So at the end, I did another 2 postdocs, more focused on volatiles on the moon and more specifically water on the moon. And then I got my permanent position as a scientist end of 2021. So it was on the topic, but it was let's say, driven by curiosity.
You actually mentioned a lot of exos, if I can call it this way. And that's also something that was confusing to me because, we talk about exosphere, and that's actually one of the spheres of Earth, but you also talked about exosphere of the moon.
Yes.
So how can we define it? Does it have similar characteristics? That's why we're calling it like that. Does the moon also have that many spheres as Earth?
No. Well, I am not an expert in atmosphere, so I will tell you what I know. So on Earth, we have different layers of different gas concentration and composition and temperature. And the last one is the exosphere, and it's very, very thin. The concentration of molecules in this layer is very, very low. And the moon is an airless body. It has no atmosphere. It has just few molecules around, so a very thin layer, very thin atmosphere that is called exosphere. So it's like the similitude maybe with the last layer of the Earth atmosphere.
Okay, but then where does the exohydrology come into play? Exohydrology is not checking the water in exosphere, is it?
As well. Exo perhaps is outer, like
Okay.
the outer layer, or the exohydrology is the hydrology in other planetary bodies out of Earth.
Okay. So it's a different out.
Terrestrial. Yeah.
I get
and
it.
one curiosity, just for you to imagine how thin is this exosphere on the moon. The pressure on the moon is from 10 to the minus 9 to 10 to the minus 12 millibar. So really high vacuum. So few molecules around. Only like a very, very thin layer.
And that's good or bad?
Yeah, it depends. Well, the atmosphere protects us from radiation, for instance, from extreme temperatures. On the moon, on the lunar poles, for instance, we have a maximum temperature around 300 Kelvin and a minimum temperature minus 250 degrees Celsius, very, very low in the permanent saddle region. So you see that the variation of temperature is really extreme, and we don't have it on Earth. It's why we can live. And also we can have oxygen. We can have another evil atmosphere as well that are not appropriate for humans, but there we have the vacuum. So it's like we are not protected against radiation. We don't have oxygen. We don't have the thermal radiation shielding and so on. So,
okay.
Good or bad?
Fun for sure. Okay, so going back to water. So we said we leave Earth right now. We go exo, as we said, but very close because it's only the moon, right? So what do we know about the water? Because I have to say that when I'm reading the news, the media, it's a bit confusing because sometimes it says, we know there is water. Sometimes it's like, we assume there is water. There might be. We're not so sure. We don't know how much. So is there anything that we can really say, we know that it's like that or not yet?
Well, I would prefer to say we believe that.
Typical scientist, oh no.
No, but there were many analyses by remote sensing missions and by return samples that they analyze water in different forms, right? And recently also they found molecular water in the equatorial regions on the moon with SOFIA telescope. And it is like, why? It is so warm there. And then the theory is that perhaps this water is incorporated within volcanic or impact glasses. So part of the mineral structure is why even if it warm up, it will not be released. So it was L-Cross mission also that it was an impactor that lift material from the lunar regolith, that it was an in situ also mission. They analyze also water and different like molecular water, different absorption bands, so linked to molecular water or to water absorbed to the regolith. Yes.
I have to interrupt you. What is molecular water?
Molecular water is H2O.
Okay.
It's water itself.
All right. Okay.
Yes.
Go on. Sorry.
Yeah, because sometimes we call water to OH and it's like hydroxyl, right? So molecular water is when we talk really about the water we know, H2O. And so there were some features corresponding to molecular water, to water absorbed to the regolith, to OH, linked to minerals or linked to metals, for instance. So, yeah, we know that there is water there and we know that there is in different forms. Also, the water that was detected on the lunar poles, this, we don't know how it's supposed to be perhaps like patchy, thin blocks of ice or frost mixed with the regolith down to 1 meter depth, 1-2 meters, depending on the authors that you read. Linked also to the as OH, like maybe a very thin nanometers or micrometers layer of hydration, like hydroxyl OH on the surface. And the permanent satellite areas, we may have frost or ice. What else? I need to recap. I have said like maybe patchy, thin blocks of ice, maybe frost mixed with the regolith, water absorbed to the regolith grains or rock grains. Also OH linked to either metals or either minerals in the surface or in the structure, and also water within the minerals. Maybe volcanic glasses or meteorite and comet impact glasses. So, yeah, there are things that were detected that we can be sure, hey, is water there and is present in this form. How much? We don't know. There are some estimations because some remote sensing missions has measured the cryosphere area on the lunar poles, and it's supposed that the water is stable at temperature lower than minus 110 Kelvin. Is the most assumed temperature, 110 Kelvin, a temperature lower than this, the water is stable. So it's okay, maybe the water is concentrated on the lunar poles, and they calculate the area where, and microcold traps and permanent shadow areas, all the area that is below of these 110 Kelvins, and then assuming that the water should be present within the first meter, and also assuming that perhaps the concentration of water, like the mean concentration of water is between, some calculation was made like with 0.1 weight percent, 10 wave percent, and 30 wave percent. I think 30 wave percent is too optimistic, but we don't know. It's like we don't know much about the abundance, about the lateral and vertical distribution, and about the form. We know that few forms exist because of some features, but we need in situ analysis really to be sure about what we are talking about.
When you say in situ analysis, so how will it work? I mean, obviously we can't find rivers, as we already said. How do you measure? You have remote sensing, that's one thing, but then you just really have to go there. Yes. What do you use? Mass spectrometer, I assume.
Well, or infrared spectrometry also, ultraviolet spectrometry, a neutron detector. This is for remote sensing. Laser spectrometer, for instance, is very useful for water because it's specific to the water molecules. Mass spectrometers, of course, because they are very sensitive and they can measure almost anything. They can measure the near surface exosphere, but also a drill can take samples or another sampling tool from the surface or from the subsurface down to 1 meter depth, for instance, and put it on the mass spectrometer and analyze the soil as well. And then you will have some mass fragment pattern that will be the fingerprint of some of different compounds, right? And depending on the mass interferences, then you can be sure that this is the compound, or maybe you can say, I have this mass fragment, but I am not sure it can be this group of compounds, for instance. And also, if you analyze hydrogen or oxygen or OH, if you don't have the molecular mass of water, you don't know if this oxygen, hydrogen, or OH is coming from water or is coming from other compounds. Like organic compounds, we don't expect much on the moon, but in the permanent shadowed areas, we can have some organic compounds, perhaps from asteroid impacts, that perhaps will give also information about the origin of life, about the building blocks of life, for instance. So we can have also organic compounds. There are many techniques, and I think all of them, they are great. They are complementary. They give complementary information. In fact, when a lander is landing on the moon, it always have different instruments that each instrument takes some measurements, and then you can combine the results from the different instruments to benchmark that what you are telling is the most probable.
And to get to, let's say, more sure results, okay? Because not 100%, that's never going to be the case. Does it mean we need a manned mission, or what we're doing right now with robotic missions is enough? And also another question, do we need to return the samples, or the measurements that we're doing without really getting it back are enough as well?
All the options are very interesting and complementary. Well, the manned missions is better, in my opinion, because you can do calibration there on site. So there is a person there looking also the observation. You can really observe what is happening and document all what is happening. And if there is one anomaly, you can link it to what you are observing. The robotic mission can also do calibration on site, but it's easier if a person is there and do the calibration on site and take a look to all the parameters. But robotic missions also, you can calibrate it on Earth, and you can send some standards there or prepare some calibration, of course, there for robotic missions. Return samples are really interesting as well, because you are going to get them here, and you have plenty of instruments in the laboratory and plenty of different experts, But you need to really be formed to don't contaminate the extraterrestrial sample with Earth atmosphere and also the fugacity. The atmosphere of Earth has oxygen and on the moon not, and then it will be oxidated and many other things. And also to don't contaminate the lab ourselves with some compounds brought from space.
Before you tell me a little bit about the missions you've been involved in, I was just wondering, I think maybe we should have started with it. Why do we care about the water on the moon? I mean, do we really need it? We always talk about, all these important minerals that are there that we want to mine, whatever, of course. Listeners know me. I'm also a bit involved in space and space resources. So that was a joke, right? I'm not using the word mining at all. But yeah, why water?
I am asked, why are you going to go to the space to do mining?
Classic question.
Yeah, and said, okay, to release pressure on resources on Earth, environmental impact also on Earth, and geopolitical conflicts, because some of the resources are concentrated in specific parts of Earth, for instance, a few things, right? And if you want to go there, you need water, because water can be used for many different things. First, for sustain life on the moon, because the goal is to build their moon village. And will be like the intermediary step to go to Mars and beyond and to mine asteroids, right? And then water is needed for sustain life, for drink water, for produce oxygen for breathe, for fuel, because you are going to split it in hydrogen and oxygen and then use it as combustible for spacecraft and also for satellites. So you don't need to come back to Earth each time, and then you save a lot of cost because you don't need to go through the gravity belt of Earth, and also you will contaminate less Earth because you don't need to launch every time rockets from Earth. So I tell fuel, life support, thermal and radiation shield. And also for the moon village, it will be important for agriculture. Also, for instance, aeroponics is one of the things that there is a lot of investigation on that as well. For establishing a sustainable robotic and human presence on the moon, we really need water. And then scientifically, it's very interesting because we can get information about the origin of water on the Earth moon system, that perhaps it has the same origin. And also learn a bit about the water cycle on the moon as a laboratory for better understanding the Earth, because the Earth is much more complex. It has rivers, it has atmosphere, it has vegetation, it has biologic ecosystems, and so it is much more complex. Organic matter in the soil, also not only inorganic matter. So the moon also can serve like, let's say, laboratory for better understand Earth.
But why? Is moon kind of related to the Earth? It's a separate body, isn't it?
Yes, it is a separate body, but one of the theories is that they originate for the Gean impact. An impactor impact the proto-Earth, and some isotopic measurements point towards that either these bodies had the same isotope signature regarding oxygen and hydrogen, or that when they impact, they vaporize and it was very well mixed, and then the moon and the actual Earth accrete. And how the water arrived to the Earth-Moon system, it can be primordial, but it can be later addition water by asteroids and comets impact. And one of the theories is that the water could be brought to the Earth-Moon system by the late heavy bombardment, that it is the asteroid bombardment created by the displacement of the giant planets. I cannot remember how much time ago. This I will not.
Doesn't matter, we shouldn't overload our listeners with numbers either, right? Yeah. Because then it's a bit difficult to follow. So that's perfect, totally.
And also, knowing a bit the water cycle on the other planetary bodies could give information about the future of water on Earth. Because, for instance, Venus and Mars were supposed to be planets similar to Earth, and we were supposed to hold water, right? And both of them, they follow two different climate scenarios. And for instance, Venus, because of the greenhouse effect, its atmosphere becomes really, really, really thick and evil, with even sulfuric acid, very acidic. And the surface temperature is around 500 degrees Celsius. And so now there is no life, there is no water there. But Mars follow another different scenario, or all the atmosphere went away to the space. And now it has a thin atmosphere, thicker than the moon, because it is 7 millibaries, but made of CO2, basically, right? And there is water on Mars, but not rivers. And the Earth could follow one of those scenarios. And knowing more about the evolution, the water cycle and the evolution of different planetary bodies, we could also know a bit more about what the future on Earth and plan for prevention or for mitigation actions.
Of course. You know, another thing that I know that not all of the experts are very fond of if I ask that question, but I have to ask it, meaning, okay, we're not sure exactly how much water we're going to get, but do we really have the technology to get the water out? Is it ready? Next day we land on the moon and we just get the water out?
Wow. It's nice that we talk about that because the extraction technology, it depends on the form of water. We can do thermal extraction, right? We can sublimate the water and collect it.
Meaning heating it up?
Yes.
Whatever you have in the sample, yeah.
Heating it up, so you transform the solid ice into vapor and then you collect it and then you froze it again, right? It's challenging to collect it because of microgravity and because of the vacuum on the moon and so on. But then we need to purify it as well. If we think about water itself, we think about warming it. Or OH, we can warm it and it is an associative desorption. OH and OH will become water and you can also collect
Associative desorption, sorry, I'm not following.
No, the associative desorption. Yeah, associative
yes,
desorption.
Yeah, you said it right, but I don't know what it is. I'm sorry.
Yeah, that is. So, for instance, there are OH linked to the surface, to the minerals. You warm it up, and then they just release the surf, but they combine together, right? There is like associative desorption because this OH will desorb from the surface, combine and create a molecule of water.
Yeah, got it.
H2O. Yeah, and so this is one thing. Then, the purification. But then we talk about water when we extract oxygen from the moon. And there are three main techniques that are in the development. But it is mostly, at least it's Eric, not me. I am working on the cryoextraction, on the sublimation, on the thermal extraction, let's say. But extracting water from the regolith, let's say, extracting oxygen. That is not water. I will tell why. It will be with regolith reduction with hydrogen is one of the techniques. There, you are introducing hydrogen and you are extracting the oxygen from the rocks and from the regolith, right? And the product is a water molecule. But it's not that you are extracting the water, you are extracting the oxygen in form of water molecule. This is one technique. Another is like the ionic liquid and the molten salt electrolysis. There are two type of electrolysis. With these techniques, you also will get the oxygen separated and then you will get the different metals or alloys of metal that you can separate by selective electrodeposition. But yeah, I am not working on that, so I cannot tell you how advanced are these techniques. But there are two extraction techniques that you are going to get the oxygen directly and one of the extraction techniques that you are going to get water. But in reality, you need to introduce the hydrogen to get this water. So in reality, the net product is the oxygen.
But for the thermal one, where do you get the heat from to heat up?
The energy.
The energy, yes.
The energy. Well, you can have solar panels, for instance, for charging the batteries, or there are some kind of domes that you can look like greenhouse effect, something like that, to warm up the regolith. There is another technique that I cannot tell much because I don't want to tell anything wrong, that they collect the thermal energy on the regolith and then they transform it in electrical energy. Then it's the radioisotopes and the nuclear, but the nuclear, I think that is for later. I think it's...
Yeah.
I'm not missing any.
I think more or less probably. I don't know.
I tell some of them.
Yeah, of course. There's probably something new that people are coming up right now as we speak, so.
But the solar energy, they are pushing really a lot for the solar energy because, for instance, there are, this is very interesting for Earth as well. There is a project, an initiative for big solar panel orbiting the Earth and transmitting 24 hours energy to the Earth, for instance. So if we develop further the solar panels to harvest the solar energy on the moon, this will have also synergies with Earth. And then we could have like a solar panel out of the atmosphere and out of all the clouds and collect energy 24 hours from 365 days per year. So
Yeah, loads of different things. And thank you for mentioning that, because it's a brilliant segue to just remind listeners that we recently talked about solar panels on Earth. But, the technology is there. There's a professor here at the University of Luxembourg, Philip Dale, that is specializing in that. So you can check that episode. And if you want to know something about mass spectrometry, we've already discussed twice mass spectrometers. So you can check that too. That was, more in relation again to Earth applications, but they are very, very interesting when it comes to unknown chemicals and trying to understand what they are and whatever with Professor Emma Szymański. So go check that out too. And I'm mentioning the mass spectrometer because I wanted to discuss a little bit the missions that you've been involved in. So we have a NASA mission and we have an ESA mission. Let's start with the NASA one. So we're talking, I always, when I mention machines or tools in a laboratory, I ask the scientists how big it is. So remember, mass spectrometer, it's not a pocket-sized machine. But in your case, what you were looking at was kind of miniaturized thing that you can take to space and do the measurements, right? What is the mission about?
Because I need to separate two things, the work I am doing now and then myself as part of the science team. So now I don't work with the mass spectrometry development since when? The beginning 2019. Now, mostly the instrumentation that I deal with is water extraction.
Okay.
Like a dirty vacuum chamber that also I will explain you more later. And we analyze extracted water with laser spectrometry. This is one thing, right? And so the mass spectrometers from those missions were developed by Open University. So how big they are? For instance, the mass spectrometer that flown to the moon early this year, that at the end didn't make it to the moon, but it took measurements between the Earth and the moon, this PTMS. The size of these spectrometers is the size of the half shoebox, is 1.6 kilograms, really tiny, and it's an ion trap mass spectrometer, for instance.
So that's, you said PTMS, just for people to know, that was a NASA mission.
Yes, it was flown as a payload in Peregrine 1 mission in January. It didn't make it to the moon, but before to re-enter the Earth, it took some measurements between the Earth-Moon space and also to get some information also about the exhaust contamination.
Okay, so that's one. But now you're also working, I mentioned it in the introduction, about the Prospect mission.
Yes.
And what's Prospect?
Before to tell you what is Prospect, I want to tell you what PTMS aimed for.
Exactly, yes, you're right.
It is
and
really
not to confuse as well.
PTMS is an spectrometer that was supposed to land on the moon and measure the exosphere, the molecules that were released from the lunar surface to the exosphere. And Prospect is a package. It has, among other things, two mass spectrometers, one ion trap mass spectrometer and one magnetic sector mass spectrometer. That means that it can also analyze isotopes. And now we know that is planned for launch in 2027, and both are part of the CLIPS initiative that are within the Artemis program, within NASA Artemis program. And Prospect is led by ESA.
Okay.
And what Prospect will do, it will drill up to 1 meter in the lunar surface in the South Pole, and it will analyze the volatiles in the lunar surface and subsurface at different depths.
And what is your role in it? Because you said lasers, and there was the spectrometers you talked about, there were no laser analysis, or is there?
No. There is not a laser spectrometer. No. One thing that we will we want to do that we didn't do still is to benchmark the extracted water from the regolith, the analysis of the isotopic analysis with a laser spectrometer and with a mass spectrometer from Open University and with our laser spectrometer. So our role there is help a bit with the calibration and with, for instance, with an isotope fractionation model. What's that? That means that when the water undergoes different physical and chemical reactions, the concentration of the isotopes, what are isotopes? Are atoms of the same element with different mass. So the different isotope of hydrogen and the concentration of the different isotope of hydrogen and oxygen change, and it's called isotope fractionation. So when we are going to measure one sample, we are going to take one sample and measure. We drill it and we take it to the mass spectrometer or to the instrument in the lander, and it will be exposed to higher temperatures than if you take it from a permanent shadowed area, maybe at 120 or 150 Kelvin, for instance, then it will be exposed to higher temperatures. And so it will likely lose a bit of water before it is analyzed. So we have developed a prototype for simulating the lunar conditions for doing the sublimation experiments or the cryo-extraction experiments, extraction of water from the regolith, both like pure ice and also icy regolith, water on extracting water from the regolith, right? And to simulate how the different physical processes will change this isotopic concentration. We did a theoretical model, and now we need to do the experiments to compare the theoretical model and the experimental model to see if it match, and to correct, like, okay, if the sample, for instance, it will be exposed to this temperature for this time and this pressure, it is supposed to lose this percent of water, right? And with this percent of water loss by sublimation, the isotope signature will be changed by this amount. And so we can correct the raw data. And also we can help also to interpret the water cycle on the moon, because you are going to analyze the lunar samples, and many other processes happen on the moon at geological times. And maybe putting all together, like how sublimation will change the isotope signature, how, the different processes, or diffusion or something like that, desorption will change this isotopic concentration. We put all together, and then we can, one, correct the raw data from future lunar missions, and two, help to constrain the theories about the water origin, water sinks, or water cycle on the moon.
How do you get actually lunar-like conditions, simulations? Do you need a special lab? Are there any facilities in Europe, or where do you go?
Yeah, so we developed something similar to the dirty vacuum chamber, but clean.
You don't want to have a dirty one.
Yeah, and also because we have two patents, one for the sublimation system, is a prototype that simulates the lunar condition, but also is like for cryo-extraction. It's both, because simulating the lunar conditions, you are going to sublimate pure ice with different ice structures, but also dirty ice and icy regolith, like regolith with perhaps 1% with different percentage of water ice, right? And so we don't reach 10 to the minus 9 millibar, but we reach 10 to the minus 7 millibars. And the temperature that we reach in the sample holder is minus 176 degrees Celsius. It's quite good, quite cold. And we can do sublimation at minus 120 degrees Celsius. For the moment. Then if in an upgraded version, maybe we can go lower. So what is special is that in the sublimation volume, the difference of temperature is only 3 degrees or lower. In the dirty vacuum chamber, for instance, one of the techniques for the cooling system is putting liquid nitrogen in the double wall of the chamber. And then you cool down the sample by radiation from the chamber walls, and then you heat the sample. But what happened that it is perhaps a difference of temperature between the sublimating volume and the walls, and maybe of 20 degrees or more. So when this water vapor is sublimating, it will deposit on the walls, and you are not going to collect it. So if you have like a microbalance incorporated there, you can study the sublimation rate, for instance. But you cannot collect the water for analyze the isotope signature. So once you collect the water, you can analyze it by mass spectrometry or by laser spectrometry, the isotopes both. And it's interesting to benchmark, to compare both techniques. Another important thing is the evacuation rate. So in our system, when the water is sublimating, since the difference is the thermal management system is cooled down and heat up by thermal conduction, and not by the chamber walls. The chamber walls are warmer, and this volume inside the vacuum chamber keeps a difference in temperature lower than 3 degrees. So when the water vapor is sublimated, it's directly evacuated and not sticked on the colder parts, because there is no colder parts. And this evacuation rate, so how fast we take out the sublimated water, need to be faster than the sublimation rate, because otherwise you will create equilibrium. And on the moon, there's not atmosphere. It's an airless body. It's an open system. That means that when the water is sublimating, it's becoming vapor, is being evacuated from this surface directly. So the fractionation will be kinetic. It will not be...
It would just fly away, you mean?
Yeah. It's like some kind... It will not create an equilibrium. It will not equilibrate. So the fractionation, the change in the isotopes, it will be larger, let's say. Yeah. And so for that, you need to also simulate. You cannot create equilibrium. You need a system who take out the sublimated vapor at least as fast as it is being generated, for instance. And then you collect different fractions, and then you can know how this isotopic concentration is changed at different temperatures, different pressures, and different amounts of sublimated water from the initial sample. You can do it with different water, ice structures, and also with water like incorporated into the regolith mixed or adsorbed, or in the mineral structure, so with different types of water also.
Okay. I'm just thinking that, we've been talking for a long time, and at the end, I think that the last subject we had, just, you explaining the whole system would be enough for the whole podcast. I would have so many questions there. It's just so fascinating. So, listeners, if you also feel this was not enough, totally contact Veneranda. I'm sure she'll be happy to explain. And then you would also get the visual part, because you don't know, but Veneranda, when she started describing, it was all, with gestures and whatever. So you would really get the whole part, and I'm sure she'll be happy to do that. But unfortunately, this also means probably you got the hint that we're slowly wrapping up. So we're coming back to the pub quiz question right now. Veneranda, if you can remind the listeners what the question was about, and then please give us the answer.
Yeah, because we have talked a lot about water,
yes,
lunar water, and how important it is for science and for in situ resource utilization, right? And we need to extract it. And we don't know exactly the amount, but we know where it is concentrated mostly at the lunar poles. So the question was, how much water do you think that the lunar polar cryospheres holds? How much water do you think that there are together in both lunar poles? The answer is from 40 million tons to 12 billion tons, depending on the concentration. If we have, for instance, 0.1 wave percent of concentration of water ice in the regolith in the 1 meter depth, or if we have 30 wave percent of concentration, that is very optimistic, the last one. But
yes, we got that already. But, just to put it in context, how much water is there on Earth?
We talk about that the Earth's cryosphere holds the 70% of the fresh water. Yeah. I don't know. I don't bear in mind the total, but I can tell you which is this 70% of the fresh water. And this means around 24 billions tons.
And we said that on the moon, if you can repeat, just to compare.
Yeah, on the moon cryosphere, we expect maximum, perhaps with the data that we have up to now,
of course,
12 billion tons.
Okay. So that means
much less.
Exactly. So, I wanted to put it into context because, of course, this is when we talk about science and big numbers, we get a bit lost, right? If you have to compare 1 and 5, you get what is bigger. But in this case, it is an exciting amount. But
1 million less.
Yeah, but it's not that much, is it?
No.
Okay, fingers crossed. Fingers crossed for sure. And dear listeners, I hope that next time you have a glass of water, you'll be looking at it in a different way. Thanks to Veneranda today, who explained a lot to us. And also remember, the moon and water, these are very, very interesting subjects. And there's still a lot to discover. Also, different planets and asteroids and everything that is there. So I can't help but get excited. Thank you so much for coming today, Veneranda.
Thank you so much for having me here.
Okay, and this is it for today. Don't forget to subscribe, to follow us, to check what we're doing. The season is almost over. So in October, we're launching season 5 of SciLux. And I can already tell you that there's going to be a few changes. Of course, we'll still be happy to be partnering up and being powered by Research Luxembourg. But I will also have something else in store for you. So wait for this space. Maybe in the next episode, I'll tell you a bit more about it. Thank you for listening. This was SciLux, and my name is Hanna Siemaszko.